Hello. Today's video will be going over glycolysis. Basically, glycolysis is there to convert glucose to pyruvate. This is done in a series of 10 steps, and glycolysis takes place only in the cytosol. The goal of glycolysis is to create energy that the cell can use, specifically ATP, or energy that can be converted by the cell into usable energy, again, ATP. So this video is going to mostly go into the specifics of glycolysis, being what steps are what molecules are at each step, what enzymes create those molecules, and what is either put in or taken out at that step. So, the first molecule is glucose. The molecular formula for that is C6H12O6, and this is the format. This is what it looks like. Typically, when we're numbering glucose molecules, we start with this carbon. So this carbon is the number 1 carbon. This one's the 2 carbon, the 3 carbon, 4 carbon, 5 carbon, 6 carbon. So there's 6 carbons. I'm not showing all of the hydrogens just because it's easier and it's a lot quicker. So, as I said before, this is a glucose molecule. So, the first step is making this into glucose 6-phosphate. So glucose 6-phosphate is basically the same as glucose, but the hydrogen up here has been replaced with a phosphate group. And that's done by putting in ATP and getting out ADP. You might be wondering, why do you use ATP in a process that's supposed to make it? Well, this allows it to change its shape and add on more phosphates, which in turn can create more ATP than was put in originally. So this is what glucose 6-phosphate looks like. I'm going to designate phosphate as a P with a circle around it, just so we don't get mixed up with phosphorus or something else like that. So the enzyme that actually changes glucose into glucose 6-phosphate is hexokinase. And I'm just going to write those in red pen. And again, ATP is put into this cycle to put the phosphorus on this, to replace the hydrogen here with this phosphorus. So that's how you get from glucose to glucose 6-phosphate. Now, the next molecule that you're going to is fructose 6-phosphate. So basically for that, instead of this carbon connecting here, this carbon is going to connect to this oxygen, and this is going to be a substituent off of this chain. So this is what it looks like. So as you may be noticing, the first step had something go into it. This step, however, does not. It's only the enzyme glucose 6-isomerase, which changes the glucose 6-phosphate into fructose 6-phosphate. So no energy is put in, no energy getting out, no other products or reactants are either put in or taken out. So, as you might be noticing, this new substituent right here looks a lot like what it looked like over here. So, as you might be thinking, a phosphate is going to come in and take this hydrogen, which is what happens. So, the only thing that did change was an addition of a phosphate here instead of the hydrogen. And that was done by adding an ATP in and getting an ADP out. So the phosphorus on the ATP was taken off. The enzyme involved in this transition from fructose 6-phosphate to fructose 1,6-biphosphate is phosphofructokinase. That enzyme is what allows the phosphorus to add here. This molecule, fructose 1,6-biphosphate, actually has the opportunity to change into 2 different molecules, but only one can keep going on, and we'll discuss that once we get there. So fructose 1,6-biphosphate can either change into dihydroxyacetone phosphate or glyceraldehyde 3-phosphate. So these are the two molecules that are made from fructose 1,6-biphosphate. They are dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. You need glyceraldehyde 3-phosphate to go on, and this is step 5, where they can change between each other. But this is the only one that can be made. These come out evenly because the molecule split in half, and so one of these molecules is made, one of these is made. But they must be in this form to go on. So to get from fructose 1,6-biphosphate to these two molecules, you need to have aldolase to convert it. And the molecule and the enzyme can convert dihydroxyacetone phosphate to glyceraldehyde 3-phosphate is trioacylphosphate isomerase. So trioacylphosphate isomerase, it allows dihydroxyacetone phosphate to glyceraldehyde 3-phosphate. Then, once that you have the form glyceraldehyde 3-phosphate, you can go to 1,3-biphosphate glycerate. Since you had two molecules here, from this point on, there will always be two molecules rather than one because you have two here. Also, the enzyme that allows glyceraldehyde 3-phosphate to go to 1,3-biphosphoglycerate is glyceraldehyde 3-phosphate dehydrogenase. So, as you've noticed, nothing has actually come off of any of these reactions that have been productive for the cell. This is the first step where something does come off that can be used by the cell. Granted, it's in the form NADH, so it has to go to the electron transport chain before it can convert it to NATP, which can be used by the cell, but nonetheless, we get something out of this reaction. So, again, from this point on, there's two molecules, so 2 NAD plus means that there's 1 NAD plus added per molecule. You're not adding 2 per molecule, so it's 1. Also in this step, you add 2 phosphates. The phosphates add to the oxygen here, and this is why you needed to add the 2 ATP earlier, so you can add on more phosphates and create more ATP later on. So now 1,3-biphosphoglycerate is created, and all it needs to do is go on to the next step. And that next step is to go to the 3-phosphoglycerate. So again, there's an enzyme that allows it to go from 1,3-biphosphoglycerate to 3-phosphoglycerate, and that enzyme is phosphoglycerate kinase. And as you might have noticed, the oxygen here is negative. It lost its phosphate group. How did it do that? It combined with an ADP. So in this step, you actually gain back the 2 ATP you lost in the 2 prior steps where you had to use it to change the structure. So at this point, you're actually up product because you're at 2 NADH and 2 ATP. Once you take out the 2 ATP you took out earlier, you're up 2 NADH. So from this point on, you don't put energy into the cell, you only take it out. So the next step is going to 2-phosphoglycerate. I forgot to mention the prior step, there are still 2 of these molecules, so I just wrote that in now. But in this step, there are 2 of these molecules as well, and this molecule is called 2-phosphoglycerate. As you may have noticed, the only difference between 2-phosphoglycerate and 3-phosphoglycerate is the swapping of places of the alcohol in this group. So this group went to the 2-carbon, and the alcohol group went to the 3-carbon, thus the name change. The enzyme that allows this to happen is phosphoglycerate mutase. As you might guess, no energy comes off of this step, because nothing is lost off of the molecule. It's simply just changing it to allow it to be taken up, to allow the phosphate group to be taken off easier and add to ADP. So now you need to convert the molecule again. You need to convert it to phosphoenol pyruvate, and that is done in this step. Now, if you're really observant, you may have noticed that the alcohol here and the hydrogen here are lost. They actually go out in the form of water. Water is a good leaving group, so it's not that uncommon for a water to be lost, or not be lost, but to be taken out of a molecule. Again, this is just because it allows the phosphate to be taken off easier, and it's just another product that the glycolysis process makes. So again, nothing else has changed. That's the only thing that comes off this step. This step actually happens because of enolase. It creates pyruvate from 2-phosphoglycerate. Without it, this step wouldn't happen. You wouldn't get the water, and the molecules wouldn't change. So, to get your last ATP, you have to change it to pyruvate, which, as I said earlier, is the final product of glycolysis. And that is done in this step 10, which is the last step. This is the infamous pyruvate molecule you keep hearing about. It has a negative oxygen, which is attached to a carbon, which is also double bonded to another oxygen. The carbon is then attached to another carbon, which is also attached to by double bond to oxygen, which is attached to a methyl group. So, as you might notice, the phosphate group here is lost, which is how that double bond gets there. It adds on to an ADP to create an ATP. And since there are two molecules at this point, you get 2 molecules of ATP out. This step can't be done without pyruvate kinase, because pyruvate kinase is what creates pyruvate from pyruvate. So, all in all, the entire process of glycolysis changes 1 glucose molecule to 2 molecules of pyruvate. You make a total, of 4 ATP, but you use 2 ATP. So, that gives you a net gain of 2 ATP. Also, you get 2 NADHs from this, and 1 water molecule. 2 water molecules. Because of there being 2 molecules here, you get 2 water molecules. All in all, this doesn't create too much energy compared to the other side, compared to electron transport chain, but it's still important because it allows the other chains to take place. So all in all, this process just allows glucose to be broken down to pyruvate, which could later be used in like pyruvate processing in the citric acid cycle, and the electron transport chain. Without this process, there wouldn't be a way to convert glucose, which is really abundant for use by the cell. So, I hope this video helped. If you have any questions, please let me know. If you liked it, just like the video. That'd be helpful for me. And if you want to know when more videos come out, just subscribe. And you should get a message about that. So, I hope you enjoyed the video, and have a great day.